So this is slideshow on Igneous Rocks Part 2. We're going to start with a little self-quiz. We'll go kind of quickly, so do your best. These are a few volcano pictures that I have taken on my travels. This first picture is Mount Rainier outside of Seattle, Washington. What kind of volcano do you think this is? If you said that it was a composite volcano, you are correct. Let's take a look at the next one. This is a small volcano outside of Crater Lake National Park, or actually it's in Crater Lake National Park, but it's outside the main part of Crater Lake. What kind of volcano do you think this is? If you said cinder cone, you are correct. It's a small cinder cone. And the area in front is basically an ash plain. The reason there's not a lot of vegetation there is because the rainwater falls very quickly through the ash and cinders, and so it's essentially a desert, even though it gets a fair amount of rain. All right, this doesn't even look like a volcano. I took it from a plane as I was flying into the big island of Hawaii. What kind of volcano is this? If you said that is a shield volcano, you would be correct. So shield volcanoes are not very volcano-like looking, at least not from the air, from a distance. They're very flat. All right, so let's look at a few other volcanic structures. In the top right, we have what's called a lava dome. This happens if you have a very sticky lava. So these tend to be felsic lavas, sometimes intermediate, but usually felsic lavas are so sticky you don't really get much of a lava flow at all coming out. Sometimes they will plug up the top of a volcano and result in a large explosion. On the lower right is a fissure eruption where a crack opens in the ground. This is the opposite type of lava. This is mafic igneous rock, which has a very low silica content, and so it's a very fluid, low viscosity lava and can form a long fracture like this, and the lava just comes spattering and flowing out. The lower left-hand corner is a satellite image of a caldera. Caldera's form, you may recall from our last lab exercise before break, when the top of a volcano essentially blows up and the magma chamber partially empties and collapses in on itself. And when it does that, it creates a huge crater, and very often it will stop the eruption of that volcano for a period of time. You'll notice in the middle of this, there is a little volcanic cone, so even after that big eruption that partially emptied the magma chamber, a smaller eruption afterwards began to build up a new volcano. And so the next picture is Crater Lake in Oregon. It's a national park, and this also is a caldera. It's a very large lake. All around the edge is the collapse edge of the caldera, and that little island in the left-hand side is a small cinder cone that grew up after that initial caldera forming eruption. So an even bigger example of a caldera would be Yellowstone National Park. Off in the distance you can see the hills. That's part of the edge of the main caldera at Yellowstone. If you ever go to Yellowstone National Park, you are actually in the caldera of a giant volcano, and that's an active volcano, and the molten rock that is still present below the surface is what produces or provides the energy for the hot springs that you can see in the foreground as well as in the distance. And so that is kind of the result of a really large caldera forming eruption. We will now move on to what's happening below the ground or below the surface, and that would be our igneous intrusions. And we have a couple pictures here from your book that I think deserve a little bit of interpretation. On the left-hand side, you see a very large igneous intrusion called a batholith. If you notice the scale down at the bottom, it shows 10 kilometers. On the right-hand side, that feature that looks very similar is called a stock, but you'll notice the scale there is only 1 kilometer. A stock would be one of the little things sticking up off of the top of the batholith in the drawing on the left. So these are our really large igneous intrusions. The largest features are the batholiths, and then big blobs that come off the top of the batholith would be a stock. And the way that these move into an area, or the way that they intrude, very often is by melting their way in. There's so much heat that they can actually melt the surrounding rock, which gets incorporated into the magma chamber, and it can melt its way up. So that's how these really large intrusions come in. So that's our batholith and our stock. This shows you kind of how that works. That's my sun there for scale. You'll notice that he's sitting on kind of a light colored rock, but next to him there's a boulder, a black boulder, apparently. And that is what we call an inclusion. And what's happened is, as the light colored rock he's sitting on, when that was molten and melting its way up, some of the surrounding rock fell into the magma chamber, and in this case that black rock did not completely melt before the magma chamber solidified around it. So that inclusion gives us a little clue as to what was around the intrusion when it was melting its way into this area. On a smaller scale, we have igneous intrusions. Very often these things will find their way through fractures in the rock, or between layers in the rock, and kind of push their way in that way. In the upper right, we have a dike. You'll notice the dike generally is a vertical intrusion, but the key for a dike is it cuts across existing rock layers. So it cuts across them. You'll notice the existing layers, probably sediments, are horizontal in that upper right-hand picture, and the dike is a wall that kind of cuts through it. In the middle on the right-hand side, you see a sill. The name might remind you of a windowsill. Sills come in and find their way between rock layers. So in this case, the sill has been injected into a weak zone between two existing rock layers. And so that's a sill. And you can see below that sill, there's actually a dike kind of feeding into that. And then on the lower right, one of the things that can happen is if enough molten rock gets pumped into that sill, it can actually start to lift up the ground surface in a dome, and that produces what we call a laccolith, and that's what you see on the lower right. It's basically kind of a sill that got a lot of extra molten rock and poofed up in the middle. And then our last intrusion is on the left-hand side, on the bottom, and that is what we call a volcanic pipe or a neck. And this is the molten rock that was actually feeding into a volcano, the stuff that cools and solidifies before it gets extruded, then becomes a volcanic pipe or a neck. So the next few slides give us a few examples of how these look outside. The first one is a series of, we would probably just call them dikes or intrusions. The black rock is the rock that was existing, that was already there. It had a lot of fractures and cracks in it. And then the pink rock is the rock that intruded it. And you'll notice that those intrusions go in many different directions. I took this picture out in Colorado. This was actually part of probably a large volcanic system, maybe even a caldera. And this is what happened around the caldera after that big eruption. The fractured rock, all the fractures were intruded, and the molten rock then cooled and solidified. So that's one potential way that something like this could occur. A more contained type of intrusion can be seen here. Now initially all these rocks look kind of gray, but you'll notice running right through the middle of the photo is kind of a black wall with cracks parallel on both sides, just behind the two gentlemen, or the gentleman in the gray coat there. That is kind of a classic example of a dike. It's cutting across the existing rock. It's a wall-shaped intrusion. This next one, we see two sills, in this case, the sills are intruding into layers of ash. This is in Yellowstone National Park. There's a sill kind of in the upper third of the photo and another one in the lower, just a little bit more than halfway down the photo. You can see it's a more resistant rock layer. The ash deposits are pretty easily eroded, and the sills, because they're solidified directly from molten rock, are more resistant, and so they tend to stand out. This is Devil's Tower National Monument in Wyoming. It is if you said that looks like a volcanic pipe or neck, you were correct. That's exactly what that is. So that's what that looks like. All of the material around it, the looser material, has been eroded and is gone. So the last topic that we want to get into is how do we then identify igneous rocks? How do we name them? And there's a lot more information on this on the website, and it's actually the lab exercise that you're going to go through. But we use two characteristics to name our igneous rocks. First characteristic is texture. And so these are examples of what we would call fine texture. Fine texture is when you cannot see the mineral crystals or most of the mineral crystals in the rock. You'll notice the texture in the middle on the right. You can see some pretty large crystals there. But in that case, most of the material is too small to see, so that's fine. And we would call that porphyritic to indicate it has two crystal sizes. The other thing that's fine but not fine is glassy. Glassy rocks actually don't have any crystals, so some people would say they're not even fine. They're their own category, and we'll see that on the table in just a moment, kind of the last slide we have to look at. Vesicular refers to vesicles, and a vesicle is just a name that we use for a bubble or a hole in the rock. So the rock on the lower left is vesicular because it has lots of bubbles in it. Coarse texture means that we can see all of the crystals in the rock. And we have three examples here. The upper right is more specifically pegmatitic because the crystals are very large. They're bigger than an inch. The lower right is kind of a standard coarse texture, which we call phaneritic. And on the lower left, there are actually two crystal sizes. Some of them are big. You can see the big white crystals. But in between those big white crystals are smaller white and black crystals that are all still big enough to see with the naked eye. So that counts as coarse texture. So the second characteristic that we look at then is composition. And igneous composition is classified as felsic, intermediate, or mafic. And we also have ultramafic, which is kind of a little special case. But felsic is pink. It has pink minerals in it. Mafic is black. That's the lower right. And then intermediate is a combination. And so the intermediate rocks are usually black and white or gray. And then last but not least, the ultramafic rocks are green. So when we put that all together, we get this table that's on page 42 of your lab book, and that you will use to do the lab exercise. You'll notice that across the top we have the composition. Felsic rocks are pink, or they have pink in them. That's the key thing. And you'll notice on this list below the word felsic, it tells you which minerals may be present. So in that list, you'll notice quartz, which is a clear crystal, but 50% feldspar with potassium feldspar, and K feldspar is pink. As we go across, you'll see mafic has calcium plagioclase, augite, and olivine, which are all very dark minerals. So that will give us a very dark rock. And then we see the top three rows are all coarse grained. So they're all, you'll notice they get the same name. We have three granites listed there. And there'll be more information on this as you do the lab exercise because the little video program I'm using is running out. So be sure to go online and start playing around with the lab exercise.